Welcome to this lecture on public versus private blockchains, where we'll walk through the core ideas, practical trade-offs, and emerging hybrid approaches. Over the next sections, I'll explain what a blockchain fundamentally is, how public and private designs differ in who can read, write, and validate, and why those choices matter for trust, performance, security, and real-world adoption. This slide strips blockchain down to its shared foundation, an append-only distributed ledger secured by cryptographic hashes and consensus protocols. Both public and private chains inherit immutability and linked records, but they make different design choices. Public networks favor wide distribution and transparent validation, while private systems use permissioning and controlled validation to meet enterprise constraints and regulatory needs. The first major fork in blockchain design is about who may read, write, and validate. Public blockchains allow any internet user to participate, relying on consensus to establish trust, whereas private blockchains gate participation with identity checks and permissions, so validation is based on authority and contracts, which has downstream implications for governance, trust models, and the system's attack surface. Public blockchains achieve censorship resistance through global node proliferation and incentive-backed consensus, like proof of work or proof of stake, producing an immutable, transparent transaction history. Their strengths are neutrality and open innovation, but they face pain points around transaction throughput and, in some designs, high energy consumption. This sets the stage for why private alternatives are often considered for performance and privacy needs. Here we highlight real-world successes. Bitcoin as a borderless value rail enabling permissionless transactions. Ethereum enabling composable DeFi apps and smart contracts. And supply chain deployments providing immutable provenance and transparent tracking. Each example shows when transparency and user empowerment outweigh raw speed, making public chains the default infrastructure for certain trust-minimized applications. The enterprise model for private blockchains centers on known validators, role-based visibility, and administrative controls for compliance. Operator override hooks and proof-of-authority consensus allow faster validation and higher throughput while trading off open participation. In practice, these systems position themselves as secure, scalable middleware that integrates with enterprise workflows and regulatory requirements. Private blockchains deliver business value in closed network settings. Interbank settlement lowers reconciliation costs and speeds transactions. Healthcare implementations enable HIPAA-compliant index sharing to improve data security and compliance, and manufacturing use cases track defective parts while protecting trade secrets, improving traceability and IP protection tied directly to measurable KPIs like latency and auditability. When comparing attack vectors, public networks defend by scale and decentralization, making 51% takeovers costly but exposing different systemic risks, while private systems focus on guarding against insider tampering through strict access logs, permissions, legal contracts, and auditable trails. Security is context-specific, so practitioners must map threat models to the chosen architecture rather than assuming one-size-fits-all protections. In terms of throughput, energy, and costs, public blockchains often amortize infrastructure and face congestion-based variability with heavier consensus energy draw and variable fees, whereas private chains can achieve kilo transactions per second with lighter consensus, lower energy consumption, and predictable fixed IT overhead. The strategic takeaway is to evaluate project lifetime volume and confidentiality needs before selecting a platform. This decision checklist helps guide architecture selection by scoring factors like participation model, data privacy, performance, compliance, and governance. The recommended pathway is to score each factor, shortlist architectures that match those priorities, evaluate the trade-offs, and then make a final decision that aligns with organizational risk appetite and operational constraints. Rather than picking an architecture based on hype, emerging bridges point toward a blended future, where public and private paradigms coexist. Sidechains provide off-chain processing, anchored to a public route for efficiency. Zero-knowledge rollups compress transactions and preserve privacy while leveraging public security, and permissioned subnets give controlled access with public auditable anchors. These hybrids promise both auditability and protection for sensitive transactions. To conclude, public blockchains offer open access and resilience with global participation. Private blockchains deliver higher speed and confidentiality with controlled access, and security choices must be scenario-dependent. Emerging architectures blur the line between these paradigms, so the strategic challenge is to revisit project criteria and ensure any blockchain selection aligns with real-world constraints and long-term goals.